solve constrained optimization problems with tensor networks, as Chiran mentioned. This work was done with our collaborators, Cheng, Peng at SLAC, who is a great resource in understanding quantum simulation problems and how tensor networks work, Siddharth, Dangwal at Chicago, and of course, my advisor, Professor Sara Achour at Stanford. In this talk, I'll be focusing on optimization problems that are formulated over discrete variables, where you have an energy function that is described in terms of what is called a Hamiltonian. This is a popular formulation often used in quantum systems, where you want to simulate and understand some chemical or physical phenomena. And it's used in other domains like Ising models or combinatorial optimization. In this setting, the overall task that you have at hand is the following. You want to find an eigenvector of the Hamiltonian matrix that has the smallest eigenvalue. This minimal eigenvalue is just the ground state energy of your system. For many of these problems, the Hamiltonian matrix and vectors that describe states can become extremely large. That is why domain specialists in quantum simulation often represent the Hamiltonian and state vectors as a product of smaller tensors. Various tensor network algorithms exist that allow you to work on solving these optimization problems while working with this factored representation at hand. Often these optimization problems, however, have a lot of implicit constraints, and frameworks and solvers for tensor networks don't often provide you first-class supports for working with these constraints. Users often end up having to manually implement these constraints themselves in the solver on how they implement the tensor network or how they encode the Hamiltonian itself. And that is what we found while talking to experts in this area. In this work, we present our DSL mask that allows you to describe such optimization problems with first-class support for expressing and efficiently using constraints. These programs can be compiled to tensor networks with our compiler, and the compiled code uses existing tensor network libraries and solvers to solve the problem at hand. So let me first lay out an example of what kind of problems are we actually interested in here, and I'll use this opportunity to explain our DSL2. Starting off, you want to find the lowest energy configuration of a quantum system. It has 4 variables. Since it's quantum, all 4 variables, for now, we can assume that they map to 4 nodes, and each of these nodes can live in superposition of one of 2 states, red or blue, and state 1 or 0 respectively. We have 4 variables, so 2 to the power 4 possible states, or 16 states in total. We represent these variables in mask as this q-bars object, which has size n equal to 4, each with d equal to 2 states. Note that we can support higher order systems as well, which is actually very common in this domain, especially used by physics simulation folks. The Hamiltonian for such problems is often defined piecewise in broken up pieces that applies local operations. In this case, it will apply an operation that will flip the color of a node if it has 2 blue neighbors. I'll first define some helper matrices that will help us describe this exact operation. You have a matrix that allows you to select your neighbor being blue or in state 0. You have one to encode the blue to red transition, and so on. You can compose them together by doing tensor products to form the overall local transition operation, and then apply them to variables 1 to 3 and 2 to 4 separately, implementing the overall Hamiltonian of the system right here. So now, in this case, I can solve this problem exactly, actually. I'll build up the full exponential sized Hamiltonian. I'll find the eigenvector that has the smallest eigenvalue. It is this sparse vector that has 3 non-zeros that I've highlighted here. It's often written in quantum notation like I've shown right here. We don't need to understand the notation for this talk. Just assume that this solution means you'll see the variables to be in all blue configuration for 50% of the time, and the second and the third node will be observed to be in red state 25% of the time each. However, this way of solving this problem was never tractable because of the exponential scaling. That is where tensor networks come in. A compiler in this case will use an iterative algorithm that will take your quantum state S, apply an operation on it, which is a function of the Hamiltonian, and give you the next state Si plus 1. All of these 3 things have to be implemented as tensor networks in this problem, and you want to slowly converge the quantum state to the ground state. The result of this algorithm can be seen as this heat map. This just visualizes the probabilities of each state across all iterations with the weights shown right here. To see if it works, we can just see at the very end, you'll see around 0.5 weight of the heat map for all blues, and around 0.25 color for the second or the third node being red. At start of this algorithm, of course, we started in a uniform mix or superposition of all states, and we can mark positions whenever we get within a certain percentage error from the solution. So at 97th iteration, we are at like around 10% error. Now, where do constraints in this problem come in? Well, constraints in these kinds of problems can come from the Hamiltonian itself. For example, in this case, if you had all blue nodes, you have two possible transitions. But if you had no node that has two blue neighbors, no transition can take place. In fact, these kind of states will have restricted dynamics. You can't really go from all states to all states at all points of time. And this is what domain specialists often exploit. For example, in this case, they'll rule out configurations that have any red-red combination that they can find. So how would those constraints be encoded? Well, one very general way would be to modify the Hamiltonian by doing regularization, which is adding some penalty terms on your energy function, artificially inflating their energy. In mask, this can be represented by adding a few lines of code that penalizes these states. On the other hand, what we can do is prune out or zero out these states that are invalid explicitly by changing the tensor network itself so that these states never show up. In mask, this is represented as the simple constraint add syntax that rules out the red-red or the 1-1 configuration that I was talking about. Here's the result of a three-way comparison. Here's the result for unconstrained solution first. We get to 10% error in 97 iterations. With regularization, we get to the same point in just 78 iterations because invalid states have been suppressed. Or you can zero them out, in which case you'll get to the same solution in only 68 iterations. In fact, if I plot the error of all these 3 points across all 150 iterations, you'll find removing these states actually results in best solution quality at all times. So how can we impose these constraints? Our compiler takes advantage of the fact that to constrain a quantum state, what you basically want to do is you want to take this vector that I've denoted out with all the names for all states, and you want to just prune out anything that has RR word in it. So you want to zero out these points that I've mentioned here. This can be basically done with tensor algebra with a sparse matrix that has non-zeros at valid points and zeros on invalid combinations. But this matrix itself is exponential in the number of variables. So again, it needs to be implemented as a tensor network. So for the constraint at hand, we'll take a look at the mask code. We'll extract out the constraint. It's this constraint that we call not equals constraint. In this case, what happens is this constraint basically says, I have a bunch of quantum variables. They explicitly cannot be in the state written on the right. That is, the probability associated with this state is 0. And they can take any other quantum state, whatever they want, in the optic process. To compile this constraint, we basically need two properties. We want to enforce this constraint locally. And in this case, it needs to be the way this constraint is implemented is we only want to accept and reject state combinations. This will allow us to build a tensor network where each variable will get its corresponding tensor, and it can communicate with its neighbors. Xi can communicate with xi minus 1 and xi plus 1. Turns out, this problem is pretty straightforward to solve because you can build a step-dependent discrete finite automata that will implement exactly that same constraint and can be mapped to a tensor network. Notionally speaking, what that means is each DFA iteration here will become a tensor in the network that I'll be talking about soon, and all transitions in this DFA will be non-zeros in the sparse tensors that get generated. For our example at hand, building a DFA could be very straightforward. You can have two states, one that says, oh, my left-hand side did not match right-hand side. That's the accepting state. Or I can have the scenario my left-hand side did match the right-hand side. That's the state we want to reject when this DFA is done. So the transitions for this could be the following. At step I, if you're in state 0, the constraint's basically already satisfied. You can stay there however long you want. If you are in state 1 and you find a mismatch, you can switch over your DFA states. Or in the case where you were in state 1 and you've again found a match, in this iteration as well, you'll stay in state 1. Now, how does a tensor come out of it? Well, at any variable, let's take the first variable for this. We have some types of transitions that are valid on your DFA. We'll start in state 1, so there's these two types of transitions. I'll build this three-dimensional tensor where there's this index bn that carries the DFA state after the current iteration will complete. So we can denote out the non-zeros of this tensor by a truth table where I'll just show the non-zero elements. First, we have a transition switching over from state 1 to state 0 whenever xn was not equal to wn. Well, that's just a singular non-zero that just says we have non-zero elements in this tensor whenever xn wasn't equal to wn and bn was 0. That is the state of the DFA after this was 0. Similarly, you can have the transition of staying in state 1 if xn matched wn. There's one other type of transitions that can show up, and those are like transitions that are explicitly not defined on our DFA. For the last variable, you have a scenario where you've matched up till now, and you explicitly want to rule out the final configuration, that is, we've matched after the DFA is complete. We write it out or express it as an invalid transition, which becomes a 0 element in the truth table, shown with the value right there and highlighted in red. So a lot of our constraints can be implemented to a tensor network through this process. There's this one other type of constraint that I'm not talking about here in this talk. Please refer to that for the paper, which can be directly implemented to a tensor network and doesn't really go through this DFA process overall. For details and proofs for some of these transitions that I've talked about and these mappings that I was talking about, please again refer to the paper. Overall, this gets us to go from a land where original constraint implementations working in this particular domain either required users to define or change how the tensor network would work with quantum number constraints, or was implemented explicitly as one-off implementations for these three kinds of constraints I show right here. And sometimes some constraints weren't even supported. The only way you could encode them out was regularization or penalization, because that's the most straightforward way one could do this. On the other hand, CoTenN allows you to generalize various constraint implementations here to a larger family of constraint expressions that we can support. Now, I can talk about how these constraint encodings improve the efficiency of tensor network algorithms and result in great performance, especially when compared to the only other general scheme we could find, which is always using regularization. For this, we'll evaluate over 2 physics benchmarks called KL and PXP right here. We don't really need to understand what the physics underneath is. And just note that they're solved, again, using an iterative tensor network algorithm. So, and I would like to obviously thank Aaron Sass at Google and Shengtao Jiang at Stanford for helping us source and understanding these benchmarks and other specialists we worked with and talked to. We run each model for different number of variables, n, and variable encoding d. These were points I mentioned at the start of this talk as things we can control on the mask code itself. And then also modulate another parameter called bond dimension. I haven't talked about it much. You can just think of it as a proxy for model accuracy. The higher it is, the more accurate your final solution will be. We'll evaluate CoTenN constraint encodings to see how it will improve DMRG convergence. To do that, we'll first evaluate our projection-based tensor network, get its final solution, use it as a target for the regularization-based run. Again, the only other general way to do this. We'll run each evaluation setting with different starting seeds. We'll then report the average reduction in number of iterations and the average simulation speedup with the minimum and maximum speedup as well that we saw across these 5 runs. I call it a simulation speedup because Julia has JIT, and we want to exclude the overheads that can come up, especially on smaller models when you're JITting a bunch of code. Here's the result. But before we dive into what the results actually mean, let me just explain how to read this plot. You have different number of variables in these different groups. In each group, we're changing the bond dimension, increasing it from 10 to 80, I think, in this case. And that's just basically increasing the solution quality as you go from left to right, making it harder and harder. Next, for our speedups, I'll show the average in this bar chart right here. And I'll show these markers to show the minimum and maximum speedup we saw across all the 5 runs. Here's our result for the Kitaev ladder D equal to 2 encoding. Just note that we generally see improving performance as number of variables increase or the bond dimension increases. This results in an overall reduction in iterations from around 8.7x to 59.5x. This roughly translates similarly to speedup from going from around 4.8x to 59.3x approximately. Then we tried a D equal to 3 encoding. Note, I told you all these quantum systems can often be evaluated for higher order systems as well. And this is one example where we are increasing the value of D. And overall, again, you see the same trend. Performance improves as you increase n and bond dimension. Here, the number of iterations goes down by around 5.1x to 21.3x. And that results in a simulation speedup of approximately going from 2.3 to 6.6x. Next, we evaluated a separate physics model. In this model, the task of interest for domain experts was to find the ground state of the system, and then the first excited state, and measure what the energy gap between these transitions is. I'll report the number of iterations for this ground state and excited state search on the left, and the result corresponding to speedup on the right cumulatively. Again, you'll see improving lines or improving bars as you increase bond dimension or solution quality. Overall, the number of iterations goes down from 10.4x to 16.7x for ground state search. For the excited state search, that goes around from 9.1x to 10x. In terms of simulation speedup, we find an overall speedup of around 6.4x to 8.6x. Overall, we find that various physics benchmarks have, especially which have these Hamiltonian-based optimization problems, have these implicit constraints. Our work enables separating these constraints out from the optimization problem at hand. Then we can compile them completely separately to a tensor network, supporting these constraints, allowing us to generalize to various other forms of constraints that hadn't been implemented before. These compiled constraint implementations can also provide you large speedups over regularization in particular, which is the only other general way to handle these things. We are currently working on building a benchmark set for these optimization problems. We are building improved tensor network implementations with specialized tensor algebra kernels that are particularly suited for working with CoTenN-generated tensor networks. In general, while working on this project, one thing I found was domain specialists often have very interesting problems and very novel solutions of how they want to solve them. Tensor networks in particular, working on quantum simulation, seem to be a very cool approach to me. And one thing I started thinking of when I started this project was how can I make their lives better, improve these tools in the first place. But what other problems can they be generalized to? What other problems exist that are amenable to solving in the same format? At this point, that's the end of my talk. I would love to take any questions. And also here's a link to my paper, by the way. But yeah.
Thank you for the talk. We have 3 minutes for Q&A.
Hello, thank you for the talk. I have a question, which is, are the tensor networks generated by your approach, or do you have any argument to their optimality or like any empirical results on that?
Thank you. That's a good question. So I think the question is basically asking, do we have previous implementations that we can compare to, or how good they are? The reason that's a good question is sadly because all of this work by domain specialists in this area is often published in like these physics conferences or physics journals. Many of them don't have implemented code that you can like find or access to. I worked with people who, helped me source these problems, told me how they don't have access to this code anymore. They've lost it somewhere 2 years ago or something like that. So that was like one big trouble in comparing a handwritten implementation that they did to an implementation that we had. I had one anecdotal example though. For the PXP model in particular, we had a implementation hand done by one person from Stanford who actually used regularization for imposing their constraints. And after a few quick conversations, we realized that for the particular encoding choice that they used, you could have implemented the same constraint that we are talking about right here. They knew how to do it for a smaller encoding. They didn't know how to do it, or they hadn't done it for a higher encoding, and they'd just given up on it. And they're like, oh, this performance seems fine to me. So that was like one anecdotal example that we found. Like, OK, we have some code, and we can compare against it. And those results will basically look like the PXP results I talked about, because that was basically their implementation then.
Hello. Hi.
Yeah.
Hi, I'm from MIT. I'm curious, in a lot of kind of continuous iterative optimization problems, sometimes you can actually get faster convergence, at least in the number of iterations, by overshooting or letting the constraints be violated, at least in the initial parts. If you think about like simulated annealing or KL annealing in training VAEs or something. So I'm kind of curious if you found, or if you have some intuition for why categorically preventing constraints from being violated, especially in early iterations, allows you to converge faster.
That's a good point. That's actually a good question, and that gets to like where these constraints actually come from as well in some of these cases. Adding constraints, especially at the start, can slow down your system, especially when you're doing regularization. But funny thing is, some of these constraints are not just for finding ground state more efficiently. Sometimes they're more like tools to search for some kind of solution that some domain expert is interested in. For example, this Kitev ladder example, the KL example I was talking about, there's the constraint basically there says that if you can swap a parameter around, you can, instead of converging to the ground state, can converge to the first excited state or the second excited state. And you can search what the overall phase diagrams or what these material properties will look like. And the problem becomes, if you're just trying to solve for, if you do that, you end up violating those constraints entirely, and then you have a solution that looks good, but is not the target that you were looking for in the first place. So these often also end up becoming just exploration tools. In this talk right now, I only focused on finding the solution or just the ground state, but in reality, the first experiment we showed was basically finding some excited state of the system. And we also like show how the solution quality that you get out of this for a tensor network is actually better and has lower errors and a better approximation quality that one could look at in the paper if they're interested in. Yeah.
All right, let's thank our speaker again.